Good morning. Today I want to talk about the general use of the Z transform. Now, we know that the Z transform is going to be used in this class for certain things, but of course it has a wider range of use. The Z transform is the discrete equivalent of the Laplace transform. And we know that the Laplace transform is used to solve differential equations. And differential equations are what we use to describe systems, right? Continuous time systems. In the discrete world, instead of talking about differential equations, we talk about difference equations. And the difference equations are what describe a discrete time system. So what we're going to do here is we're going to take a simple system, we're going to describe it with a difference equation, and then we're going to use Z transforms to solve the equation. So as I said, the Z transform is used or can be used to solve difference equations, and the difference equations are what are used to describe these discrete dynamic, in other words, time-changing systems. Let's start with a simple example. Let's say we're going to write a difference equation that describes a bank account. So specifically, let's say you're going to open a bank account. You're going to deposit initially $200 in the account. Every month, you're going to deposit $10. And the question is, how much do you have in the bank in 10 years if the monthly interest rate is 0.3%? Now, this is not realistic. 0.3% is very large. But let's just suppose this is the interest rate. And we want to find how much we're going to have in 10 years. Now, if there was no interest, and we knew we had $200 initially and we're going to deposit $10 a month, we could easily calculate what we're going to have in 10 years. The thing is, since this is a compound interest, the interest is calculated every month, would have to go, if we weren't going to use Z transforms, would have to calculate it month by month and do this for 10 years. We don't want to do this. We just want to use Z transforms to give us an equation where we can find out how much we have in the account for any month. So like I said, let's start off writing the difference equation that describes this bank account. Now, since we're starting out on this, our systems are going to be relatively simple. We're only going to look at one input, one output systems. So let's define the input and let's define the output of our system. Now, since this is a bank account, the input is going to be how much money we deposit into the account. Now, what we want to know is how much money we have in the account. So that's going to be our output. And we're assuming that we don't take any money out during these 10 years. So writing the input is X. Writing the output is Y. We can write the following thing, right? If X is the input, then X of N is going to be how much money we deposit, right? It's going to be 200 for N equal to 0, and N in this case is going to be the month 0, month 1, month 2, month 3, month 4. And we deposit $10 every month after that. Now this, instead of writing it, right, N equal to 0 and N greater than equal to 1, we can write it as this here, right? It's 200 delta N plus 10 mu N minus 1. Or if we don't want to mu N minus 1, we can write this as 190 delta N plus 10 mu of N, so that both start at 0. And so at 0, we have 190 plus 10, which would be equal to 200. And for every month after that, this is 0 and we have $10. Now let's write our difference equation that describes our system. Okay, how much do we have in any month? In any given month, how much do we have in the account? Well, the amount I have this month is the amount I had last month, because we're not taking out any money, plus the interest that it's accumulated, plus whatever we deposit new in the account. Okay, so what we have this month is what we had last month, plus the interest, plus the amount that's deposited this month. So this is how we write it out. Of course, the interest is calculated in how much we had last month. So that's going to be 0.003, because it's 0.3%, times how much we had last month. So this is the equation that describes how much we have in the account during any month. Now, joining the first and second term here, this would be our difference equation. Y of n equals 1.003 y of n minus 1 plus x of n. Now, we want to use z transforms to solve this equation. So what do? Well, we take the z transform of this equation, right? Y of n is going to have z transform y of z. So this term we write as y of z. Now what do we do with the second term? We know from our study of the properties of the z transform that if we multiply by a constant in time, we multiply by the same constant in the z transform. We also know that if we shift by 1, right, remember the shifting property? If we shift by 1, we multiply by z to the minus 1 in the transform domain. So y to the n minus 1 transforms into z minus 1 y of z. And then x of n is just x of z, and we know that a summation in time is a summation in the z transform. So this is going to be our equation in the z transform domain. And we want to solve it. Now, to solve it, of course, we have to write our x of n as x of z. This is x of n in time as we had calculated it above. Now we can calculate the z transform of each of these terms, right? 190 delta n is 190. 10 mu, actually this should be mu of n. There, that's better. So then 10 mu of n is going to be 10, 1 over 1 minus z to the minus 1, magnitude of z greater than 1. So this is going to be our x of z. And so if we substitute that in our equation above, this is what we get, right? Let's put both y of z's on the same side. So we get this on one term, we can factor out the y of z and get this. And then we have our x of z on the other side. Now, let's put everything over the same denominator, and so we get this. Solving for y of z, we get the final equation we have here. And we see it's going to be a z transform with two poles, and we know how to take inverse z transforms. One little thing, this y of z is going to have two poles, one which is due to the input, the other which is actually due to the system we described. Of course, we have to look at the region of convergence to know how to take the inverse z transforms. The region of convergence of x of z is z greater than 1 and r of y. Now r of y, we'll look at this later on in more detail, but for now, if a system is causal, which all of our systems are going to be causal, the region of convergence is greater than the pole, so it's going to be z greater than 1.003. We do our inverse z transform as we've always done, right? We have two poles, so we're going to have three systems. We do a partial fraction expansion. We calculate the constants, a0, a1, a2, as we did before. a0 turns out to be 0. a1 is going to be 3,533.3333. And a2 is going to be minus 3,333.3333. So this is going to be our y of z. Since the region of convergence is greater than 1.003, we know how to take the inverse of each of these things, right? Again, this is a constant that comes down. The inverse of this is going to be 1.003 to the n mu of n. And the inverse of this is just going to be 1 to the n mu of n. Now, this equation, if we look at it, will give us y of n for any n we want. So we can calculate it for month 0, for month 100, for month 1000. Now, we might as well evaluate and make sure this is right. We know that at month 0, we should have $200 in the account. And right, if we substitute n equal to 0 here, this is going to be 1, this is going to be 1, and so we'd have 3,533 minus 3,333, which will give us $200. So this is correct for at least y equal to 0. Now in 10 years, it's equal to 120 months, and since n is the months, we'd calculate y of 120, so we'd get basically this. Substitute n equal to 120, and we see that we have $1,728 in the account, which after having 10 years of doing something, only having $1,700 in the account, doesn't seem to be the best way. What I'm trying to say is either you have to deposit more than 10 bucks a month, or you have to look for a higher interest rate. Let's do another one. Let's write a model for the number of students in Circuits 1 in the Electrical and Computer Engineering department, our department. This comes from actual numbers in our department. So how many students are going to be taking ENEL 3105? Now, these are historical data. Year to year it might change a little bit, but historically we've had about 220 new students a year. Now let's presume that all of our students get to Circuits 1. Of course this is not true, some of them leave, some transfer, but let's say all 220 students get to Circuits 1. Let's say that 42% do not pass the class. Again, this is from actual data, looking at many years over many professors. Basically 40% of the students who take Circuits 1 don't pass the class. So let's assume it's 42% do not pass. And let's say that everyone who doesn't pass takes the class again. In other words, the people who don't pass, none of them leave the university or go to another major. And the question is, how many students will be taking Circuits 1 in 10 years? You know, is this going to grow and become infinite, or is it going to stay a finite number? So again, let's define our input and our output. Let's say the input is the number of new students coming into the class, right? What we're describing is Circuits 1. The input is going to be how many new students come in. In the output, what we're going to be measuring is how many students are taking the class. Now, pause it if you need to. Write down what the equation is. Now, how many students are taking the class this semester? And in this case, n of course is not going to be months, n is going to be semesters. So how many students are taking Circuits 1 in a given semester? Well, it's going to be all the new students who come in, which is x of n, plus the students who didn't pass last semester. And the number of students who didn't pass last semester is 42% of those who took the class last semester. And so that's why it's y of n minus 1. We convert this equation to the z transform. Again, so as before, y of n minus 1 is going to be z to the minus 1 y of z. X of n is going to be x of z. And this would be our equation after taking the z transform. The region of convergence of y is, again, greater than the pole of the system. The input, x of n, let's simplify this a little bit. I said there were 220 students each year. Since we're talking about semesters, let's say half of them take it the first semester, half of them take it the second semester. So there are 110 new students every semester. And so we take the z transform of this, which would give this here, with a region of convergence z greater than 1. Now substituting that in the equation above, this is what we would have. Again, multiplying numerator and denominator by z. In this case, we would get this equation here for y of z. And again, we have two poles, so we're going to have three terms in our partial fraction expansion, and we can get the a's as we always do. Verify that I've done this correctly. And this is going to be our y of z after we've found the coefficients of the partial fraction expansion. Since the region of convergence is magnitude of z greater than 1, this is going to be our inverse, right? 0.42 to the n mu of n times this constant. Here it's just going to be 1 to the n mu of n times this constant here. And again, we can verify, right, if we substitute y of 0, the first semester, since there were no students before, we should only have 110 students. And we can see that if we substitute n equal to 0 here, we're going to get 110 students. So after 10 years, how many students do we have taking the class? Now, I'm forgetting about summer. Let's simplify this a little bit. Let's say there are just 2 semesters a year. So 10 years would be 20 semesters. And so we're going to calculate y of 20. If we put y of 20 here, basically 0.42 of 20 is 0. Basically it goes to 0, it's very small. So we're going to get basically 189 or 190 students. And actually this is the number of students, very close to the number of students who actually take circuits 1. So this model, although relatively simple, accurately reflects what's happening in circuits 1. Now, I want you to do this for homework. So we're going to have a totally fictitious scenario where we have an infectious disease. Right? You're going to write a model of this infectious disease. Let's say there's an outbreak of an infectious disease. Now let's say that 10,000 people are infected before a cure is found. Okay, let's say some people are not practicing social distancing, and each person that's infected infects one other person per day. This is not a great amount, but let's say if you're sick, you're going to infect one other person per day until you're cured. And let's say that 20% of the people are cured every day. Okay, and we want to know how many infected people do we have in 10 days. This is a relatively simple model, but as you can imagine, there are people who are writing complicated models of what's going on with COVID-19. This would be a simple example of that. So how many infected people do we have in 10 days?